Okay, today we're looking at stability and equilibrium. So first of all, here's a bit from the notes, and you'll notice that I've taken these from my notes. So you've got the missing words, I should say. The missing words are filled in there. So we've got stability, basically. So if we have something that, say, here's the base, and here's the base, there and there, and if something, the weight force acts from the centre of gravity, and so in this case it's acting from the middle, and if the weight force is acting through that base, then the thing's stable and it will fall back, and that's kind of this is that left hand one here. However, if the as you can see here, on the right hand one, it's unstable and falls over, essentially because down here our weight force is acting here. Here's the corner of it outside of that, and so it's then going to fall over. So there's two things that it depends upon, and that would be the width of the base and the height of the centre of gravity. So the wider the base, then the lower the centre of gravity, the more stable something will be. Alright, so the next thing we move on to is what we refer to is equilibrium. Alright, equilibrium. So there's two types of equilibrium. There is rotational, so whether something is going to rotate or not. And the key thing about there is that the net torque, QUE, net meaning the sum or all, sum of all your torques, is 0. Alright, so it won't rotate if the sum of all your torques is 0. So that's one type of equilibrium. The other one we call is static equilibrium. Oh, I think I need to go back and redo that. That's terrible, even for me. There we go, equilibrium. Static equilibrium, so there's two things that we need here. And the net force has got to equal 0, and also the net torque. Has also got to equal 0. All right. So if those things are true, then it would be in static equilibrium. Little thing you've got to be a little bit careful of with this static equilibrium thing is that it may not necessarily be stationary. All right, may be moving with a net force of 0 and a net torque of 0. All right, let's have a look at some examples. So the first example I've got is a person standing on a beam. So let's have a look. All right. So here's our example. So I've got a person, 50 kilogram mass, standing 1 metre from the end of a 3 metre beam. The mass of the beam is 40 kilogram. Calculate the reaction at support A and support B if the system is in equilibrium. Alright, and there's a note there that the weight of an object such as a beam acts from the centre of mass / gravity. In this case it's from the centre of our beam, so our weight force on our beam acts here. Alright, the beam is 40 kilograms, so our weight force of our beam then will be the 40 kilograms times the 9.8, of course. Alright, we've also got a person that's standing here, and they're 50 kilos, so that's 50 times 9.8 for theirs. Alright, now there's two forces acting, because the beam's supported at A and at B, so there's what I'm going to call RA and RB, reactions at each. Alright, so first of all it's asked for the reaction at support A. So since both of these are not known, what we can do is, to assist us, is we can take a point of rotation wherever we like, basically. And so what I'm going to do is going to take point of rotation here about B. Alright, so if I take the torque about B, then we've got torques in a clockwise and an anti-clockwise direction. So this RA will be in the clockwise direction, and these ones here will be in the anti-clockwise direction. So what do we get? So clockwise torque, so this is about B for our rotation. Better go to the next page. It's going to be very messy if I do it there, so let's take that out. So about B. So clockwise, and because it's in equilibrium, it equals anti-clockwise. So let's have a look. The clockwise ones, I said that was RA. Now, because that beam is 3 metres, then its distance from the point of rotation, which is B, is 3. So it's RA times 3 equals. Alright, the anti-clockwise rotation. Well, there's two things doing that. That's these two here that I did. Alright, and the person is 1 metre, so this is 1 metre in here, and the middle of the beam, if it's a 3 metres, then that's 1.5 there. Alright, so my anti-clockwise ones, let me just go back, is 40 times 9.8 times 1.5. So 40 times 9.8 times 1.5. And to that I've got to add the other one, which was 50 times 9.8 times 1. Alright, so 3 times the reaction at A is equal to, alright, so 40 times 9.8 times 1.5 is 588. And 50 times 9.8 times 1 is 490. When we add those up, 588 plus 490 1078, divide that by 3, and the reaction at A is 359.3 Newton. All right, so that's the reaction at A. We're also asked in the question for the reaction at support B. So now there's, again, we can do the talk about A, or, and I've done in the notes, I've done it using the talk, but what we can actually do is we can go that force up equals force down. Now the force up is the two reaction forces, and the force down is our two weight forces, so 40 times 9.8 and 50 times 9.8. Now we've just figured out that the reaction down is 359.3 plus the reaction at A, I should say, not down, and then 40 times 9.8 is 392, and 50 times 9.8 is 490. So when we add those two together, or B then would be 392 plus 490. Forgot me 2 there. 392 plus 490 minus the 359.3. And so the reaction at B ends up being 522.7 Newton. All right, and in the notes on the website, I did that, took talk about A to get that. Now, also looks like on the notes on the website, I've been a bit bad and used 10 for the acceleration due to gravity, which it's not, of course, it's 9.8. All right, let's have a look at our next example. All right, here's our next example here, figure 5, that's that there, concrete beam. For a lookout, the beam's 4,000 kilos, it rests with no connection onto pillars X and Y, and then hangs out a bit. All right, so with no understanding on the lookout, what is the force of the beam on support X? All right, so we've got this force F mentioned up there, but we've also got for Y, and there would be a force there, but we don't know what it is. So the best thing that we can actually do then is to take Y here as our point of rotation. So we're going to rotate about Y. All right, so when we rotate about Y, and remember this person's not standing there at the moment, so it's just the beam. So if we're taking about Y, we've got two forces. We've got our weight force over here, and then we've got this other force here, the one that we're looking at, the support at the beam. So we need to do torques, and from that we need to know that distance there. So it looks like our 8 plus 4 is 12 metres for the whole beam. So half of 12 is 6, and so the distance between Y and the weight force would be 2 metres. All right, so let's go to the next page so I can write it out. So we're looking at our clockwise torque equaling our anti. clockwise torque in this case. So our clockwise torque, that's our force at X, times the distance that X is from Y, which we're shown on the diagram of 8, so the force at X, then the 8. And then in the anti-clockwise direction, it's this one here, which is the weight, and the weight is 4,000 times 9.8, and the distance it is 2 Newton. And so when we figure all of that out, or actually I can do fx if I divide by 8, on both sides, and then we can go 4,000 times 9.8 times 2, and then we divide that by 8, and then we get 9,800 Newton. All right. The next bit says, what is the maximum load that can be placed at Z, point Z there, so the maximum load here, so we'll call that at there the F force at Z, which would be the weight, of course, sorry, a bit vague there, so that's the mass times G, whatever that load, and that's the load that they're talking about there. Assume launch without the beam tilting, so we don't want the beam to actually tilt. So there's a couple of ways that we can do that, but the main way that I can do that is again taking talk about Y. So if we're talking about the beam not tilting, so what that means is that it's effectively this force here, the lowest that this force here could be before the beam actually tilts. So there's some contact and the beam's pushing on there, and so it's getting pushed up. So that's if this force here was equal to 0. So we'll go to, again, about Y. And so again, we're looking at clockwise, equaling anti again. Spelled it wrong. There we are, that's better, anti-clockwise. So our clockwise force. So making it go clockwise now is this force here, Fz. So F at point at Z times the distance, and Z hangs over 4 meters, equals the anti-clockwise torque, and that's this one here again, that weight. And that weight's 4,000 times 9.8, and it hangs over 2 meters. Yeah, it hangs over 2 meters from Y. All right, so when we figure out what that force would be, and we would do that by Fz dividing both sides by 4,000 times 9.8 times 2 over 4, and that comes to 19,600 Newton. So if we wanted to know what the load was in kilograms, we'd go 19,600 divided by 9.8, and so the most we could put there would be 2,000 kilograms. All right, okay, so there's one more example. Okay, so here's the example. Says street lamp mass 20 kilos. So if that's a mass of 20 kilos, then that force down here is 20 times 9.8, which is 196 Newton. Assuming that mass of both the rod and the wire are negligible, the rod which is straight is hinged at C. So hinged at C, there's a key word there, hinged at C. So that means we're taking our rotation here about this point right there. Makes an angle of 30 degrees to the light pole, as shown in figure 3. Okay, so assuming that the pole's vertical, and the weight force, of course, acts vertical as well, then if this here is 30 degrees, then this here also is 30 degrees. Okay, and then this here would be 60 degrees. All right. Calculate the magnitude of the force in cable AB. Right, so if cable AB wasn't there, that would swing around. So there is a force in cable AB acting that way. Call that F. All right, now the length of the rod's not specified, so I'm going to call it L, and I'm guessing because it's not specified, that's going to cancel out somewhere. So let's have a look at what we would do here. All right. So in the notes there, I've drawn a nice little diagram that shows that in a bit of a different way. But anyway, what we're going to do is we're going to talk about QUE, about C. So we're again looking clockwise equals the anti-clockwise. All right, so clockwise, what's going to make it go in the clockwise direction? Well, what's going to make it go in the clockwise direction is this force here. So it's 196 times L, but also we've got to use a direction because the angle between the force and the pole of length L. And so the direction between those is 30 degrees. So what that means is my clockwise force is the length of the pole L times the 196 times sine 30. All right, then the anti-clockwise force is that red one. And again, same thing, the length times the force times the sine of 60 this time. So we got the length times the force, which is what we're trying to find out, times sine of 60. And as I mentioned earlier, and I was hoping that they cancel out, which they do. So my force in my pole then will be 196 times sine 30 divided by sine 60. And when we do all of that, we end up with 113 newtons. Now, of course, there were some decimal points there, but I just rounded it off to the 3. All right. All right, so what that brings us to is the end of that lesson 19. So there's problem set number 19. Now there's also, we're due for a test on this last area of things that we have done. All right, so that would be the impulse, momentum, and torque. So, any questions about anything that needs clarifying there, make sure you ask me, and good luck with the questions.